quickly. Okay, Chemistry 3101. Let's start off with a little bit of review from Chapter 2, because in Chapter 2, we covered the concept of functional groups. We learned a bunch of functional groups like amides and aldehydes and ketones and esters and carboxylic acids, thiols, sulfides, etc. And so I have a molecule here. It's kind of a neat looking molecule. And there's a few functional groups in this molecule. I'll give you a second to look at it. You can see it's got a ring in it. It's got some heteroatoms. Remember, a heteroatom is anything that isn't a carbon or a hydrogen. So you can see that it's got 3 oxygens in it. It's got a nitrogen in it as well. And if you understood bond line structures, you should be able to identify all the carbons. I'll just scribble them in here in green quickly. We have 1, 2, 3, 4, 5, 6, 7, 8, 9. So there's 9 carbons in this molecule. And of course, you have to understand bond line structures in organic chemistry. Okay, I'm going to go ahead and delete all those carbons. And another thing you've got to be able to do are to identify lone pairs. And remember that oxygen, when it has no charge, always has 2 bonds and 2 lone pairs. And thus we could put in 2 lone pairs on every one of the oxygens in here. And remember that nitrogen, when it has no charge, it always has 3 bonds and 1 lone pair. So we could put the lone pair in on the nitrogen. Could anybody just yell out or identify a functional group that's found in this molecule? Any functional groups in here? You could type it in the chat or unmute your mic.
Is amide one of them?
An amide? So there's no amide in this one, because an amide, so if I put in amide, an amide is when we have a carbonyl, so carbon with a double bond to oxygen, and then it's going to have a nitrogen directly attached to it, like this. And then there's going to be R groups coming off of the carbon and 2 R groups coming off of the nitrogen. And we do have a nitrogen here, but you can see that on this carbon that's attached directly to the nitrogen, there's no carbonyl. And thus, we don't have an amide in here. Somebody says a carboxylic acid. Also, there's no carboxylic acid in here. So carboxylic acid is when we have a carbonyl and it's bound to an oxygen, but directly bound to that oxygen, we have a hydrogen. So we have an R group on the carbon, and we do have a carbonyl here, and we do have an oxygen bound to it, but we don't have a hydrogen here. We have a carbon here. Exactly. And so if we have a carbon there and not a carbon, not a hydrogen, that would be an ester. So if we put a circle around, I mean, technically it's all of this. So the R group, and then we have the carbonyl, and here we go. So we have an ester here, because an ester, so an ester is when we have a carbonyl with an oxygen directly attached. It's attached by a single bond, and we have 2 R groups. Right? The difference between the carboxylic acid is the carboxylic acid has an acidic proton attached to this oxygen, and an ester has an R group. Okay, so we identified ester. I see that Kiana put in amine, and Kiana is correct that there is an amine right here. Okay, and technically you could cover the whole R group. You could just circle it like this, and that would suffice. So this is an amine. And remember, an amine is when we have an R group attached to a nitrogen. You could have hydrogens attached to it, or you could have, R groups attached to it. And if you watched my video, you'll see that I cover the difference between a primary, a secondary, and a tertiary amine. And so if you have 3 R groups on your amine, that's considered a tertiary amine. If you only have 2 R groups on your amine and you have 1 hydrogen, then it's considered secondary. And if you have 1 R group and 2 hydrogens, then it's considered a primary amine. But for our first quiz, all you really need to know is amine. So we have an amine. Okay, what else? There's 2 more functional groups in here. Could anybody identify any other ones? There's not an aromatic in here because an aromatic, so if we have aromatic is when we have double and single bonds alternating in a six-membered ring. So we would have a double, single, double, single, double, single, like this. Here, yes, exactly. Here we have a six-membered ring, but it just has one double bond in it. And so this would be an alkene. Yes, absolutely. And there we go. So functional groups will not be on quiz 1. This is chapter 2. All right, the last one is an ether. Yes, absolutely. We have an ether right here. And so this would be an ether, because an ether is when we have an R group and then an oxygen and then another R group like that. There we go. So we identified all 4 functional groups in this compound. We have an amine. Technically, it's a primary amine because it's got only one R group attached to it. Then we have an ester, an alkene, and an ether. Okay, let's try another one. Take a look at this interesting compound right here. This compound, I'll give you a second to take a look at it. And if you can identify a functional group in there, don't hesitate. Yeah. Okay, I'll give it a, so yeah, a carboxylic acid. Exactly. There's a carboxylic acid in this molecule. The carboxylic acid is right here. So carboxylic acid. I saw that somebody put alcohol. There's no alcohol in here, and it might be a knee-jerk reaction to say, well, I have an OH, therefore I have an alcohol. Something you've got to do in organic chemistry is take what I call the 30,000-foot view. If you just see an OH by itself like this, you might think, well, there we go. I have an alcohol, but you remember, you have to look at the entire picture. And you see that the carbon that's directly attached to the OH or the hydroxyl has a carbonyl on it. And so we have to take both of those things into account. And so when I have something like this, I have a carboxylic acid. I saw that somebody else said a thiol, and the answer is absolutely correct. We have a thiol here, because remember that a thiol is just the sulfur analog of an alcohol. There's one more functional group in this one. I'll give you a clue. It's this one right here. It's when we have a nitrogen, exactly, with a carbonyl attached to it. This is an amide. So we have an amide in here. Another thing that you want to be able to do in organic chemistry is put in all the lone pairs. There's a bunch missing in here. We're missing 2 lone pairs on the sulfur, 2 lone pairs on this oxygen, 1 on this nitrogen, 2 on this oxygen, and 2 on this oxygen. Just out of interest, could anybody tell me how many carbons are in this compound since we studied bond line structures? How many carbons are in this compound? Yeah, absolutely. Absolutely. There are 6 carbons in here. Yes. We have one, I'll use the red pen. We have one here, one here, one here, 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 and here. So there's all of our carbons. So we have 3 functional groups. We had a thiol, an amide, and a carboxylic acid. And the last one is this compound here. And I'll just help you out with one of the functional groups. Whenever you see an R group and you have NO2 attached to it, this is called a nitro. And this is a nitro functional group. It's found in things like TNT and nitroglycerin. And so we have a nitro group right here whenever you have an NO2. But there are 3 more functional groups in here. Could anybody identify any of them? Again, don't hesitate to unmute your mic. Yeah. I think we're in the right vein here. Yeah. Excuse me. Can anybody identify any other functional groups in here besides an aldehyde? There's one that big 6-membered ring that alternates double, single, double, single. Yeah, that would be an aromatic ring. Absolutely. So we have an aromatic ring right here when we have a 6-membered ring that alternates. So this is aromatic. aromatic. And then we have an aldehyde right here. So this is an aldehyde. And there's one more. There's one more in here. Could anybody? Yeah, absolutely. It's an alcohol. Yes. Here we go. So this is an alcohol. There we go. So we identified all the functional groups in here. Yes, the only functional group that I didn't cover in the chapter 2 lecture that we did the other day was the nitro, but I'm covering it with you now. And what's cool about nitro is that it's got a neat Lewis structure. If you draw the Lewis structure of a nitro, it's actually got a charge on the nitrogen and one of the oxygens. It looks like this, where you have a negative charge on the oxygen, but you have a positive charge on the nitrogen, and they cancel out. So the charges cancel out. So we end up with something that's neutral. So there you go, a nitro. And nitro comes up a lot in organic chemistry too. It doesn't really come up in organic chemistry 1 unless we're specifically talking about functional groups. But there you go, some functional group practice. And where we left off last lecture was talking about resonance, and we were talking about the allyl carbocation. And if we look at this carbocation, remember that when you have a carbon that's got a double bond attached to it, a double bond, okay, so if we draw this, we could put in all the hydrogens. We have a hydrogen here, 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 and then we only have 2 here because we have a carbocation. So what I'm getting at is that each one of these carbons is sp2 hybridized. All carbons are sp2 hybridized. Now, I'm not going to draw in the sp2 orbitals. That's neither here nor there. I'm not worried about those at the moment because it doesn't help me explain resonance. But what I do want to draw is the unhybridized p orbital for each one of these carbons. And we looked at drawing orbital overlap diagrams in chapter 1. And so we have a p orbital here. We have a p orbital here, this carbon, again, because it's sp2. And we also have a p orbital here. And since you have 3 p orbitals that are on adjacent carbons, what they actually do in reality, it doesn't look like they're touching here, but we know that they actually are touching each other. They're all touching. And what that does is it allows the 2 electrons in this pi bond to be what we call delocalized between all 3 carbons. And so that the 2 electrons in that pi bond are not stuck in this one spot. They're not localized here. They're actually shared across all 3 carbons. Now, how would you draw that? How would you show somebody that those 2 electrons are shared across all 3 of those carbons? Well, one way you could do is by drawing a resonance hybrid, and I'm going to get to that in just a second. But the more common way, and what we're more interested in chapter 2, or most interested in, I should say, would be to draw a resonance structure where we show the pi bond on the other side, and we put the positive charge over here. Now, if you're thinking, Mr. Dion, all you did was flip this molecule around to end up with this molecule. Well, that's not true, because if I number the carbons, 1, 2, 3, 1, 2, 3, then we can see that the pi bond in the first structure is located between carbons 1 and 2. The positive charge is on carbon 3, and you can see that the positive charge and the pi bond have switched places in the second structure. Now, again, the resonance structures that we show here, the ion, or the allylic, or the allyl carbocation, is not vibrating between these 2. It's not that the electrons are vibrating between the 2. That's not what's going on here. It's that I'm trying to draw a resonance structure on paper, and there's no way, or it's very difficult a lot of times for me to just draw one structure that encompasses all the resonance structures. And so we draw a collection of resonance structures, and that way we see, or we can visualize, how the electrons are delocalized throughout the allyl carbocation. Now we can draw what's called a resonance hybrid, and I'm going to talk more about that later. But a resonance hybrid, resonance hybrid would look something like this, where you would draw 1, 2, 3 carbons, and instead of putting a positive charge on carbons 1 and 3, what you would do is you would just write partially positive, and this is partially positive because the 2 carbons split that positive charge. And then instead of drawing a pi bond here or a pi bond here, what we say is those 2 electrons are shared between all 3 carbons. I've been teaching organic chemistry for years, and I've never asked a student to draw a resonance hybrid on a quiz. However, I always assign problems from the textbook where it asks students to draw a resonance hybrid. Why would I do that? Because I think it's a good idea for students to practice drawing resonance hybrids, even though I don't ask them on quizzes. And normally the reason I don't ask it is because sometimes they're difficult to grade. Sometimes they might not be drawn so well because they're, maybe a little bit more complicated to draw. But that was kind of where we left off last class, is talking about resonance. And so today what we're going to do is we're going to talk more about resonance. We're going to take a look at what are called curved arrows that in resonance structures aren't demonstrating the flow of electrons, but enable us to show how the electrons are delocalized throughout the resonance structure. And we're also going to take a look at some rules for drawing resonance structures, some rules. So to enable us to be able to identify how would you draw a resonance structure. And then later on, we're going to look at a bunch of different resonance structures for the same hybrid. And we're going to say, well, which one of these would be the greatest contributor? Which one would be the greatest contributor out of all these resonance structures, and which one would not be so much of a contributor? Okay, well, let's go back to our slides here, see if I can find where I left off. Here's our functional groups, so I'll just throw the nitro in here. We'll put RNO2, nitro. There we go. So now it's officially in the list, and let's scroll down and find out where we left off, and it was around here. So let's just review pi bonds and or formal charges in resonance structures. They're more spread out than are implied by this structure right here. And so what do? We use resonance structures to fully represent how the electrons and the positive charge are spread out throughout the allyl carbocation. So we took a look at the 3p orbitals, and here is an even better picture, if you can believe it, than what I drew this morning, because we can actually see those 3p orbitals overlapping, and instead of the 2 electrons from the pi bond being stuck here or here, those 2 electrons are actually shared between all 3 of those unhybridized p orbitals. We say that they are delocalized electrons. And we took a look at the resonance structures here. And just some other finer points is that when you're drawing resonance structures, you must have the square brackets around your resonance structures, and you must draw a resonance arrow. So this is a resonance arrow, which is a double-headed arrow. Again, and I went over this last class, if you draw this for a resonance arrow, that is not resonance, that is equilibrium. That's something you would have seen a lot of in general chemistry too, when you talked about equilibria. I'm sure you did a whole chapter on equilibrium constants. And then I took a look at the resonance hybrid with you this morning, and I can't emphasize this enough, that these 2 structures are not vibrating or switching back and forth. They help us to understand or to represent the overall resonance hybrid. All right. And I went over the analogy of a nectarine, or I think it was a mule that I talked about last class. And here we go. Now, if you're wondering, why does this happen? Why is resonance important? Here's the answer, is that when we have electrons that are more spread out throughout a molecule or an ion, it stabilizes the molecule. When they have more room to move, the electrons, it stabilizes them. I told you this. Electrons are like hyperactive children, and if they can move, they will, and they like to move around. So here we go. That is why resonance occurs. It serves to stabilize the molecule. And we talked about the delocalization of charge as well as the electrons. So the charge is actually spread out over the 2 carbon atoms rather than either of them just having a full +1 charge. Okay, so let's start something new. It's Thursday morning. Let's take a look at what are called curved arrows. And we're going to be using curved arrows throughout all of Organic Chemistry 1 and Organic Chemistry 2. You got to understand curved arrows and know how to use them. And when we draw a curved arrow, like you see right here, you can see that it's got two parts. It's got a tail and it's got a head. And when you have a double-headed curved arrow, like this, you can see that's got a double head. That represents the flow of 2 electrons. Okay, so it represents the movement of 2 electrons. And if you're wondering, well, can you show the movement of 1 electron? The answer is yes. If you draw what's called a fishhook arrow, so this is called a fishhook arrow. This shows the movement of 1 electron. But this isn't covered until chapter 10, so don't worry about this at all for chapter 2 or for chapter 1, even for the next month. You don't have to worry about fishhook arrows. Only double-headed arrows because they show the movement of pairs of electrons, 2 electrons, or a pair. Anyhow, it says the arrow starts where the electrons are currently located and it ends up where they're going. All right, and we're going to explore curved arrows to show reactions in chapter 3. But again, I cannot stress this enough. In chapter 2, we are not using curved arrows to show reactions, just using them to draw resonance structures. That's it, nothing more than that. So let's talk about what the rules for curved arrows are. If there's one thing I've learned teaching chemistry, is that students tend to like rules. They say, you know what, Mr. Dion, tell me what the rules are. I will follow those rules, and then I'll get a good grade. And I don't think there's anything wrong with that. I like to follow rules in chemistry too. So let's take a look at what the specific rules are for using curved arrows to describe electron delocalization, which in turn describes resonance. Rule number 1. So what's the first rule? Never show a single bond as being delocalized. In other words, don't break a single bond. So a single bond or a sigma bond, we're not breaking any bonds because if you think about what breaking a bond means, breaking a bond represents a reaction, right? What's a chemical reaction? That's when you break a bond and then you make a bond. And so we're talking about resonance in chapter 2. We're not at reactions yet. And so do not be breaking any bonds when you're drawing resonance structures. Again, single bonds are going to break in chemical reactions, not in resonance. So don't start snapping them and breaking them all over the place. Here we go. What else? Rule number 2, never exceed an octet for a second row element. If you exceed an octet for elements like boron, carbon, nitrogen, oxygen, and fluorine, that is a big no-no. Remember that I told you there's no such thing as a carbon with 5 bonds. If you ever end up with a carbon with 5 bonds, you've done something seriously wrong. What could I use here? The blue highlighter. Put a big X over that. We'll put a big no. You cannot have 5 bonds to carbon. And similarly, you can't violate the octet rule for nitrogen and oxygen and fluorine. So let's take a look here. It says the maximum number of electrons that are available for second row elements, since they only have 4 orbitals, 1 2s and 3 2p's, is 8 electrons. Once you get to the third period, sure, yeah, then you can have more electrons. You have the 3 d orbitals available, but not for these elements. You do not have those. And so if you take a look at these curved arrows, I always laugh whenever I get to this slide. I always think of bad arrow, you know, like shaking your finger at it. Bad arrow, because I have a 18-month-old daughter, and my 2 older kids are always going to her, bad baby, you know, so bad arrow. But let's take a look at this arrow right here. What is so wrong with this arrow? And do not draw this, okay, because this is a heresy, and you wouldn't want to be, you know, one of those people that goes around writing down heresies like your instructor is going to do right now. And the only reason I'm doing this is for demonstration purposes only. But you see how the tail of this arrow, is starting on a pair of electrons, and the head of the arrow is ending, is ending up between 2 nuclei, between the carbon and the oxygen. And remember that the arrow represents the flow of 2 electrons. And so what would you get from this? The carbon would still have the 3 bonds to hydrogen, but you'd take a pair of those electrons and you'd make a new bond and you'd be left over with 2 lone pairs. Now you've got 5 bonds on a carbon. That is a bad arrow, my friends. Let's put a big old X over that because you cannot do that. That is a huge no-no. Do not do what Mr. Dion is doing. Exactly, Alexandria. It would cause the carbon to have 5 bonds. That is a big no-no. Cannot do it. The next one is another bad arrow. Okay, why is this a bad arrow? Well, you see, and I'm just going to explain it a little differently this time. You see the nitrogen here is surrounded by 1, 2, 3, 4, 5, 6, 7, 8 electrons. Everybody's happy, right? The nitrogen is surrounded by an octet. But if we take a pair of electrons from the oxygen and we make a new bond here, then the nitrogen would be surrounded by 10 electrons. That's impossible. It cannot happen. So we have this, and again, don't write this down. This is, I'm committing some kind of crime. The Department of Homeland Security is going to show up in my office here any second. That is wrong because you can see the nitrogen is surrounded by 10 electrons. And we saw the same thing here around the carbon. These are bad arrows. I don't like the cut of this jib, okay? The next one, another bad arrow, again, because you would exceed the number of electrons that are possible to have around an oxygen. You can see that the oxygen has 1, 2, 3, 4, 5, 6, 7, 8. If you were to make a new bond here, it would be surrounded by 10 electrons, and therefore that is a bad arrow. Let's just put an X over it here. Let's stop drawing these hermetical structures. And the last one, it's a little bit more difficult to recognize it here, isn't it? Because now you have a bond being created between this oxygen and this carbon, but you've got to train your mind's eye to know that you've got 2 hydrogens on here. So the carbon does have an octet. 1, 2, 3, 4, 5, 6, 7, 8. And thus, if you were to put a double bond here, whoa, that is a big no-no because you already got those 2 hydrogens here. Okay, if you were to do that. So I'm going to leave the formal charge. But anyhow, that's just a bad arrow. So let's just not even write that down. All right, give me a thumbs up if you follow me on bad arrows and exceeding the octet rule. You don't want to break the octet rule. Great. Yeah. I mean, think about it. There's nothing easy in organic chemistry. Something you're never, or hopefully never going to hear me say is this is simple. This is easy, okay? Organic chemistry is not an easy subject. However, hopefully you do remember the good old octet rule from General Chemistry 1. Somebody says rules were made to be broken. You know what, Andrew? That would be one of my mantras. I like breaking rules, but unfortunately, in organic chemistry, there are exceptions to rules, but not the octet rule, not for boron, carbon, nitrogen, oxygen, and fluorine. Just, you know, Andrew, that makes me think of something. Just as an aside, and this is just, you don't have to worry about this for not directly for the first quiz, but you remember the octet rule? Learning that in Gen Chem 1, the octet rule, and I bet you some of you would have learned that in high school. Well, they teach you the octet rule and say you got to follow the octet rule. You got to follow the octet rule. Well, there's actually very few elements in the periodic table that follow the octet rule strictly. Very few. Like really, it's only carbon, nitrogen, oxygen, and fluorine that cover the octet rule because boron is in group 3A, so it's can only be surrounded by 6 electrons. Hydrogen doesn't follow the octet rule. Helium doesn't follow the octet rule. And once you get past fluorine, well, then you have the 3D orbitals available. So yes, the octet rule is definitely a thing, and we see it a lot in organic chemistry because we deal with carbon, nitrogen, and oxygen and the halogens like fluorine constantly. But it's a rule that doesn't work all the time in chemistry. Anyhow, that's just kind of a fun thing. Let's move on here. Here's something that you can do, though. It says second row elements will sometimes have less than an octet. That's totally cool. An element can have less than an octet. That's no problem. It will develop a charge, but we only can't exceed the number of electrons. Take a look at this resonance structure here. There's nothing wrong with this resonance structure. If you take a look at this molecule, and this is acetone, right, which is nail polish remover, so it's CH3 with a carbonyl. Oops, that's not, I'll put that lone pair closer to the oxygen. Son of a gun. There we go. And this CH3. So this is acetone here. There's nothing wrong with this curved arrow that's drawn here. It's taking the pi bond and it's breaking that pi bond, not a sigma bond, not a single bond, breaking the pi bond and then putting the 2 electrons on the oxygen. So then now the oxygen has a formal charge of -1, right? The oxygen has 6 valence electrons, subtract 1 stick and 6 dots gives you -1. And then the carbon has 4 valence electrons, subtract 3 sticks and 0 dots, and that gives you +1. And thus the oxygen and the carbon, their negative and positive charges, respectively, they cancel each other out. So there's nothing wrong with the curved arrow here, because the carbon has less than an octet, but that's totally cool. Nothing wrong with that at all. No violation of the octet rule there. Well, let's take a look at a practice problem here and see if we can identify the violations. We're like organic chemistry police officers or something. See if you can identify the violation, okay, that's occurring here, and describe the violation. It's like writing a ticket for these curved arrows. And some of them, I can see that not all of them are violations of the octet rule or violations at all. Let's take a look at A. Could anybody tell me, and it's not a trick question, you know, every once in a while I'll have a student that thinks I'm always trying to fool my students. I would never try to fool a student. I'm just plainly asking you, could anybody just describe quickly what the violation is in here? Yeah, rule 2 is violated. Somebody else put 10 electrons around nitrogen, violating the octet rule for nitrogen. Alexandria, Nicole, Coy, Angel, Andrew, you're all 100% correct, right? You see what's totally going on here. And we'll put here, let's just make it simple. We'll write would exceed an octet of electrons on nitrogen. There we go. Good enough. So perfect. And my students, man, you guys answered that super quickly. So that's great. What about B? Any violations here? This curved arrow? Yay, nay? And go back into the chat here. Yeah, Andrew, I think you're completely correct. There's no nay, I like it. But yeah, there's no violation here. No violation. And so we could actually draw the other resonance contributor. So let's just put a closed bracket here. We'll draw a resonance arrow. We didn't touch this double bond. And so now we would have this resonance contributor, but now we would have formal charges. We would have a positive charge on the carbon, and we would have a negative charge here, but there's no violation here. So yeah, it has, the carbon has, we'll put here, carbon has less than an octet, but that is okay. Nothing wrong with that. And then the last one, C. What's the, any problems with C? Do you see any problems in C? Yeah, yeah. I'm just watching the chat here to see if, yeah. Okay, this one does have a violation. Now, the reason why it's got a violation is because you've got to remember that when you're looking at a bond line structure, this carbon has 3 bonds, but there it's implied that since it's got no charge, that there is a hydrogen attached to it. Exactly, exactly, Andrew. And so if you were to draw this resonance contributor, and I'll just say it doesn't happen, okay, this is a big no-no, and don't draw this because it's sinful. Okay, I'm breaking some kind of laws here. You would actually end up with this, where this carbon would have 5 bonds, and we'll put here, that is a no, no, no. You know, I think Destiny's Child used to have a song. You can say no, no, no. You can say yeah, yeah, yeah. Well, this is a big no, no, no. So this is what Beyonce was singing about, was that you cannot exceed an octet of electrons around a carbon. Okay. Well, what do you think? Give me a thumbs up if you follow me on the violations. Like, I don't want a thumbs up violations. Those are bad. Yeah, well, as long as you understand them. Cool. Yeah. All right. So, excuse me. Violations of the octet rule, recognizing when we're not violating the rules. Okay. Now, if you've been practicing your bond line structures, your formal charges, your functional groups, all those kinds of things, you're going to be able to identify formal charges and resonance structures pretty quickly. Remember our last class, we went over the bonding patterns of nitrogen and oxygen and carbon. So we said, and let's do it. Let's go back. We got time. Where were they? They were over here. Remember this? We talked about when oxygen has 2 bonds, 2 lone pairs, it has no charge. When oxygen has 3 bonds and 1 lone pair, then it has a +1 charge. And when oxygen has 1 bond and 3 lone pairs, it has a negative charge that never changes. Then we talked about nitrogen. When nitrogen has 3 single bonds, no lone pairs, it's +1. When nitrogen has 3 bonds and 1 lone pair, it has no charge. And when nitrogen has 2 bonds and 2 lone pairs, it has a -1 charge. What your goal should be, and what you will be able to do after you've practiced enough, is you'll be able to look at an element, a carbon, a nitrogen, and oxygen very quickly and determine its formal charge without doing any kind of math or without thinking too hard. It's just recognition. You'll see it so many times that you'll eventually get the hang of it. So let's go back and take a look at this slide here. It says, when using curved arrows to show resonance, the structures often carry a formal charge, and you've got to draw in that formal charge. So let's draw what the question mark, what the answer would be. I hate these question marks that they put in the book, but the question mark is actually going to equal this. So let's just draw the skeleton first. Oops. Let's draw the skeleton, the parts of the molecule that aren't changed. There we go. And so we took the first curved arrow, taking this pair of electrons and making a bond between the carbon and the oxygen, comme ça, like this. And then the second curved arrow, this one took the pair of electrons from the pi bond. So it takes these 2 electrons. I know that the arrow isn't touching the pi bond. I know it's not actually touching it, but that's what it represents. And you can see that the arrow is ending up on this carbon. So that means the pair of electrons are ending up on the carbon. So we've got a pair of electrons here. Now, could anybody tell me where the formal charges are in here? And again, it's not a trick question. Just throw me an atom and tell me what the charge would be. Oops, sorry, I'm having a stroke. Come on, you. There we go. Hey, yeah, excellent. Yeah, I saw that somebody said a +1 on the oxygen. That's perfect. Absolutely. There's a +1 charge here. I'm going to write it in red. And again, we know that when oxygen has, let me write it down here. When oxygen has 3 bonds and 1 lone pair, it has a positive charge. Whether it's like this or like this, it's still going to have a positive charge. And then any other ones? Any other formal charges in here? Are there any other formal charges in here, right? If we have a positive charge, that must mean there's a negative charge because you're starting with something that's neutral, right? This molecule is neutral. Exactly, exactly. So if this is neutral, that means that this has to be neutral. And we have a -1 charge over here. Exactly. All right. So you see, well, let's take another look at it. So all we're doing is we're not breaking any of the rules, and we're showing what the resonance contributor would look like. So this first curved arrow is showing the movement of these 2 electrons, and they're going here. So that means that you're going to form a bond right here, and then the lone pair will be gone. And then this second curved arrow shows the movement of the electrons from the pi bond, and you're taking those 2 electrons and putting them down here. So you get rid of the pi bond, and that is this compound that I have drawn here. But now we use the formula for formal charge. The oxygen has 6 valence electrons. Subtract 3 sticks, subtract 2 dots, which gives you +1. And the carbon, remember that there's a hydrogen drawn in here, or implied. It wasn't drawn over here, is it? We just erase everything on here. There is a hydrogen atom right here. And so now this carbon, this one here, has 3 bonds and 1 lone pair. So we take 4 minus 3 minus 2, which gives you -1. Yes, since the tip of the arrow, right? Look, the tips of these arrows are very different. This tip is ending up between 2 atoms. This tip of an arrow is ending directly on an atom. So if it ends up between 2 atoms, you make a bond. And if it ends up on an atom, you're going to be making a lone pair. Okay, there we go. So formal charges. All right, well, let's move on to section 2.10, and we're going to talk about resonance pattern recognition. Again, students tend to love rules, and I do too, because it enables you to just memorize a few short things that enable you to solve a lot of different problems. And now we're going to look at the 5 general bonding patterns for resonance, the 5 general bonding patterns. And we're going to look at all of these in detail. The first one is an allylic lone pair. In fact, we just saw that in the last example. Then we're going to talk about allylic carbocations. That's the first thing I showed you, was the allyl carbocation. We went over that. Something that's going to be new would be a lone pair next to a positive charge, or a lone pair next to a carbocation, I should say. The next one is a pi bond between 2 atoms with differing electronegativities. We saw that one this morning too. And the last one, which we haven't looked at yet, is conjugated bonds around a ring. And you can see that this applies to aromatic compounds. So let's start with number 1, and we'll make our way all the way through to number 5 and see if we can figure some of this stuff out. But before we get into pattern 1, we need to know what allylic means, or what allyl means. And in order to understand that, our textbook introduces 2 new terms. The terms are vinyl and allyl. And you've probably heard of vinyl before. You've heard of things like PVC, polyvinyl chloride. Well, that involves a vinylic, what's called a vinylic polymer. That which is neither here nor there for today, but you need to know what a vinyl and an allyl position are. So check this out. When we're talking about vinylic positions, so vinylic refers to the carbons that are involved in a pi bond. You see that we have a carbon here and a carbon here, so we call those vinylic positions or vinylic carbons. Once you go 1 atom away from the carbons that are in the double bond, so here's our 2 carbons of the double bond, you go 1 atom away, and any one of these carbons here, or any one of those positions, we call those allylic positions. Okay, so the reason we called this an allyl carbocation, right, is because you had a pi bond and then you had 1 carbon away from it. So we call that an allyl group. All right, so you got to be able to recognize allylic positions and vinylic positions. And if you remember, it says here that you've got to be able to recognize allylic lone pair. So what's an allylic lone pair? Well, we just talked about what an allylic position is. And if there's a lone pair on an allylic position, then we can draw a resonance structure. Take a look at this molecule right here. You can see that we have a double bond right here, but what's an allylic position? It's when you have a double bond and then 1 atom away from the allylic, or from the double bond. Whether it's this one, this one, this one, doesn't matter. So we have, carefully, we have the double bond. Let's start over here. We have 1 atom away where I have the circle. And let me put a triangle around it. That is an allylic position. Is there a lone pair there? No lone pair at that position. So there's no resonance structure I could draw there. However, if you look on the other side, here's our vinylic carbons. Here's an allylic position. Is there a lone pair in that position? Yes. Therefore, I can draw a resonance contributor. It isn't shown here, but we're going to practice drawing them in a second. And so you see that this lone pair is not allylic to a pi bond. However, this lone pair is allylic to this pi bond. Give me a thumbs up if you follow me on the concept of an allylic lone pair. We have a double bond. We go to the neighboring atom. If it's got a lone pair, it's considered an allylic lone pair. Cool. All right. Well, it says here that all of the lone pairs drawn in all of these molecules and ions, they are all allylic. And so what we want to do is we have to show the resonance delocalization of a lone pair. And in order to do that, you always need two curved arrows to show resonance of an allylic lone pair. Now, normally we write resonance structures going from left to right, just like we read the English language. But since I set this slide up kind of, in a funny way here, what we're going to do is we're going to draw them going vertically, okay? So let's start with the first one, this guy right here. We're starting right here. We have an allylic lone pair. So I'll draw my closed bracket like this. These are vinylic carbons. This is an allylic hydrogen. There is no lone pair on the hydrogen. There's none here. There's none here. But this is an allylic carbon. It also has two hydrogens bound to it, but it's got a lone pair. Is that an allylic lone pair? Yes, it's an allylic lone pair. And thus, we can draw a resonance contributor. We use two curved arrows. We take the tail of the arrow, we start on the lone pair, and we make a bond between this carbon and this carbon. But that would give this carbon, that would render it a Texas carbon, or give it, or it would exceed the octet rule. And so we have to break this pi bond, and we're going to put that pair of electrons on this carbon over here. Let's draw what that would look like. We have our three carbons like this. Now we have the double bond here, and we have the lone pair over here. So now we've got the negative charge on this carbon. And so that is our resonance contributor for our allylic lone pair. Give me a thumbs up if you follow me on that resonance structure. The first one. If you have any questions, just stop me. Okay, let's move on and try the next one. I'll use the blue pen just to kind of clear it up here. So we've got a double bond. Now we're going to move a little bit quicker. You can see that there's two lone pairs in the molecule, and they happen to be at the oxygen, which is in the allylic position. This is a vinylic carbon. So we go one position away. That renders this oxygen allylic. And so we draw a curved arrow. We take one of the pairs of electrons, and we make a new bond between the carbon and the oxygen. It could be that lone pair. It could be this lone pair. That doesn't matter. And now we're going to break the pi bond so that we don't exceed the octet rule on this carbon. And we're going to put the pair of electrons on the other carbon. Now we're going to draw what the resonance contributor would look like. In fact, I think we drew something like this already this morning. And it's going to look like this, where we have the lone pair down here. And now we have the positive charge on the oxygen and a negative charge on the carbon. Like that. Maybe I'll use my blue pen again. Like that. Okay. The next one. Do we have an allylic lone pair? Yes. We have a double bond. This is an allylic position. There's no lone pair on it, though. This is an allylic position, and it does have a lone pair on it. Therefore, we can use two curved arrows. Start with this one. We're going to make a bond between the carbon and the oxygen here. But that would give this carbon 10 electrons. And so we're going to have to break this bond and put a pair of electrons up here. You can even put in the lone pairs that are missing, like that. And now we're going to draw the other resonance contributor, which is going to look like this. So we're going to have this, and then we'll have a double bond here, like that. Now, I have a question for you all. If I highlight this carbon in orange and this carbon in green, could anybody tell me which one of, if I highlight this oxygen in yellow and this oxygen in green, could anybody tell me which one of these oxygens would have the positive charge? Would it be the yellow or green? Yes, absolutely. It's the green one. Absolutely. So we have the positive charge here, and we have a negative charge up here. Let's move a little faster. If we look at the next one, missing a lone pair here, but this is our allylic lone pair. I'm going to close the bracket up here because we're drawing resonance structures. We're going to take the lone pair, we're going to make a new pi bond here, but that would exceed the octet rule for the carbon if I didn't break this bond and put the pair of electrons up here. So now we've got this, and we've got the nitrogen with two lone pairs on it, like that. And now the negative charge is on our nitrogen. And for the last one, could anybody identify the functional group in this molecule? Just a little functional group practice. Yeah, it's an amide, absolutely. Yeah, it's an amide. Okay, cool. So, and we can draw a resonance structure for just a plain old amide, just a regular old run-of-the-mill, everyday normal amide. We put our pi bond is here. We have a lone pair here, so we use the same old pattern where we're going to take the lone pair and make a double bond here, and we're going to take the double bond and we're going to break it. And now we can draw the resonance contributor, this, and now we've got the oxygen, which is going to have a negative charge, and we have our nitrogen, which will now have four bonds attached to it, and so it's going to have a positive charge, like that. And there you have it, folks. Allylic lone pairs, and we were able to draw resonance structures for each one of these compounds and ions that has an allylic lone pair. All right. I see that somebody says, I'm understanding most, but not all of this. I would say that is completely normal. In order for a student to understand, to be able to understand something just by watching me do it, I would say is next to impossible. Next to impossible. You have to try it yourself. The only way you can master drawing resonance structures is to practice drawing them. Okay, I don't want to sound like a broken record, but just, has anybody read all of chapter 2 yet? I'll just ask you just for fun. Has anybody read the chapter 2 in its entirety? Okay, I saw a couple of people give me a thumbs up. First of all, before you come to lecture, I would recommend always reading the entire chapter. If you just come to lecture and listen to me talk about things, you can learn that way for sure, but really that's kind of like jumping into an ice cold swimming pool. You want lecture to be more like a hot tub where you're more relaxed and you're filling in the blanks. And so I think it's helpful to read the textbook before coming to class so you have the crux of what we're going to learn or what we're going to cover in the lecture, and then I can clear up anything that you don't understand. And if you read all of chapter 2, there's one part in the textbook where he says, and I don't have it with me right now, but anyhow, there's a part in our textbook where he says, organic chemistry is like riding a bicycle. Can you learn how to ride a bicycle by watching YouTube videos and watching somebody else ride a bicycle? Can that be done? I would say no, that would be impossible. You cannot ride a bicycle by watching me ride a bicycle. You could watch 1,000,000 hours of people riding a bicycle on YouTube and read about it in a book, but you'll never master, or you'll never even learn how to ride a bicycle. And so when it comes to drawing curved arrows, you've got to practice drawing curved arrows for resonance. It's the only way to learn it. And that means, and again, I'm repeating myself, but you can't be afraid to make a mistake when you're drawing your curved arrows. It happens to everybody, but once you get the hang of it, it gets easier and easier as you move along. Okay, well, let's take a look here. It says when the atom with one allylic lone pair has a negative charge and is delocalized, as is shown here, then we still end up with a negative charge, and that makes sense, right? If you're starting out with something that's negative, you have to end up with something that's negative. Same thing here. We have a negative charge. We have to end up with a negative charge. So that's something else to look for. If you're starting it with something that's neutral, then if you're making a formal charge, that has to be balanced out by an equal and opposite formal charge. So if you're starting it with something that's neutral, like what I have in the green circle here, and you're making a positive charge, well, then you've got to have a negative charge to balance that out. Because when you're making resonance structures, you're not creating any new charges. All right, well, let's move on to the next one, which is the allylic carbocation. We've covered this one quite a bit. In fact, it was the first type of resonance structure that I showed you, where we have three p orbitals on, or three overlapping p orbitals on consecutive carbons or atoms. And it says here, if there are multiple double bonds, then you can keep drawing resonance contributors if those double bonds are conjugated. Conjugated means nothing more than having a double bond followed by a single, followed by a double, followed by a single, double, single, double, single. That's what conjugated is. For example, an aromatic ring is conjugated because it goes double, single, double, double, et cetera, et cetera. And so if you take a look at this allylic carbocation right here, you can move these pi electrons between these two carbons to make a new double bond. But remember that this carbon has one hydrogen attached to it. So when you move those electrons, now this carbon still only has that one hydrogen. And since it's sp2 hybridized and only has 3 bonds, it's going to have a positive charge. Well, we've also got another pi bond here, and so we have a second allylic carbocation, and thus we can draw another curved arrow going in this direction to fill in the missing electrons here. And so now, since this carbon only has one hydrogen, we're going to have another positive charge over here. And so you've got to be able to recognize when you form a new allylic carbocation, and you can draw a second resonance contributor, and so on and so forth. The next one is a lone pair adjacent to a carbocation. This is something that we saw this morning when we looked at acetone. If you're wondering why I keep writing out acetone every time it shows up, so this is acetone here. The reason why is it's a very commonly used solvent, especially in the organic chemistry lab. If any of you take the wet lab for organic chemistry, you use acetone as a solvent from time to time. Excuse me. But here we have a lone pair. We actually have 3 lone pairs here, but they're adjacent to a carbocation. And so you can take one of those lone pairs and you can fill in the empty p orbital. And here you end up with acetone, which has no charge. But here's another example down here where we have a carbocation and we have a pair of electrons here. And so you can take that pair of electrons and you can fill in that empty p orbital. And what's cool about this is that here the carbon does not have an octet, and here it does have an octet because it has a hydrogen here. And so it is surrounded by an octet of electrons, and the oxygen is surrounded by an octet both here and here. So we're going to take a look at rules that help us to determine whether something is a greater contributor to the resonance hybrid than something else. And this would be a greater resonance contributor because everything has an octet. Anyhow, I'm getting ahead of myself. What's next? A pi bond between atoms of differing electronegativity. Here we have an oxygen, which has an electronegativity of 3.5, and then carbon has an electronegativity of 2.5. We have a pi bond between the two. And so you can always break that pi bond and put the electrons on the more electronegative atom because it's got a greater desire to hold those electrons. And so there's nothing wrong with this resonance structure right here. And that brings us to the last pattern that we need to be able to recognize, and that's conjugated pi bonds in a ring. So this is something that we see with aromatic compounds, And check this out. When you're drawing an aromatic ring, you can draw the aromatic ring like this, or you could draw it like this, where you have this, like this. These are identical to each other. Why is that? It's because all of the pi bonds in an aromatic ring are conjugated. Everything is conjugated, right? It goes double, single, double, single, double, single. And so you could draw 3 resonance arrows simultaneously, which show how all of the electrons in the pi bond are completely delocalized. We're forming a new pi bond here. We're forming a new pi bond here and here. You can see them formed over here. And we lost the pi bond here, here, and here. And you can see there's only a sigma bond here, here, and here. And there you go. And it says the pi bonds can be pushed from clockwise or counterclockwise. It doesn't matter. You end up with the same thing. And I can prove that to you. If you take a look at these 2 structures here, in this resonance structure, they drew all 3 of the arrows in a counterclockwise fashion, but we can also draw them in a clockwise fashion. And how would we do that? Well, let's draw a resonance arrow first like this. And we could draw them going like this, and like this. And it would give you the exact same thing. So there you have it. Those are all 5 of the patterns that you need to be able to recognize. Just to recap, they're all summarized on this slide right here. The allylic lone pair, the allylic carbocation, a lone pair of electrons adjacent to a carbocation, a pi bond between 2 atoms with different electronegativities, and conjugated pi bonds in a ring. And that's something that we see with aromatic compounds only. All right, so where were we? Somewhere around here. We were at this problem here. Just let me double check here. So what I want to do is I want to take a break and give you a chance to try this problem. It says, practice the act of recognizing patterns of resonance using curved arrows to push electrons and show their delocalization. First thing I'll ask you is, are there any allylic lone pairs in here? Before we take our break, I'll just ask you, is there an allylic lone pair in here anywhere? Anywhere at all? Yes, no? Yeah, absolutely. Hey, Alexandria, I see what you said. She says, yes, on the oxygen. Absolutely. Yes, there's an allylic lone pair. Any one of 3 of these, it doesn't matter. They're all identical. But yes, we have an allylic lone pair. So we know we could draw a resonance structure here. Hey, I get another one for you. Is there a pair of electrons adjacent to a carbocation anywhere in here? Yeah, absolutely. Yes. So we'll put here, we'll label this as lone pair next to or adjacent to carbocation. So I'll just put C+ for a carbocation. Okay, so what I want to do now is take a break, and I'm going to give you a chance to work on this, and it won't take you, the entire break to do it, but see if you can find and draw any resonance contributors here. Remember that when you draw them, in order to draw them properly, you've got to have an open bracket like this. You've got to draw a resonance arrow, and you've got to show the flow of electrons. So you have to move a pair of electrons like this, and I'm not going to draw them just yet. I want you to give them a shot. Try it yourself. Again, it's like riding a bike. You've got to try it yourself to see if you can do it. There's one other one in here, isn't there, that I didn't bring up? One other pattern that you might recognize in here. But again, we'll talk about that after the break. What time is it? It's 9:14. So why don't we come back? Let's see here.